As a final example of one of our summation notation formulas, we have the following theorem. So it says that the sum I equals 1 to n of I cubed is equal to n plus 1 over 2. Now you're thinking to yourself, wait a second, that looks familiar. That's just the sum from I equals 1 to n of I, and that is correct. But we take that and we square it. So the sum from 1 to n of I cubed is equal to n times n plus 1 over 2, quantity squared. So for example, if I sum 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed all the way up to 10 cubed, I plug in 10 for this formula on the right-hand side, so I get 10 times 11 divided by 2. 10 over 2 is 5. 5 times 11 is 55. So this is all equal to 55 squared. So you can check that out and see if it works. So 55, you square it, and that's the same as this over here. So we're going to do a very nice, clever geometric proof of this formula. Now this proof, as it turns out, is more than 1,000 years old. So this proof has been known about for over 1,000 years. And the idea is to take a big square, and we're going to have a bunch of little pieces. So the first one is a square of side length 1. And then what we'll do next is put another piece, and then this length from here to here has length 2. And then we'll have another piece with length 3, and so forth. And then a piece, so this side here has length 4 like that, and then so forth until we have finally, it's not to scale, but we have our nth piece like that. And the whole idea is to show, and by the way, these little boomerang shaped guys, these little L-shaped boomerangs, that shape there is known as a gnomon, or gnomon. I'm not sure if this is G silent or not. The gnomon. And so the idea is to find a formula for the ith boomerang, the ith gnomon. So the ith gnomon is going to be a shape that looks like this. Right. And the length over here is going to be I, and the length on this side is also going to equal I. And the idea is to show that the area is just I cubed. So the total area here is I cubed. So we'll call that G sub I. So this would be G sub 1, G sub 2, G sub 3, G sub 4, all the way up to G sub n. So the idea is to show that the area of the ith gnomon is I cubed. And so the sum from 1 to n of I cubed has to equal the total area of this square. Now, the side length of the square is just length 1 plus 2 plus 3 plus 4 plus dot, 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 plus n. So the total side length here is n plus 1 over 2. And similarly, 1 plus 2 plus 3 plus 4 plus dot, 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 plus n is just n times n plus 1 over 2. So you have a square with side length n plus 1 over 2. So the total area of this shape is given by the right-hand side, n plus 1 over 2 quantity squared. And since the area of the ith gnomon is I cubed, that area has to equal 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed all the way up to plus n cubed. So we get the formula being true, as long as we can show that the area of G sub I is I cubed. So we already have some of the dimensions. We know that this is length I, that's length I. Now what about, so let's draw in the missing square. So the missing square basically has side length, well, it has pieces, right? It has 1, 2, all the way up to I minus 1, right? So this is going to be the sum of the sum of j from 1 to I minus 1, right? So this is going to be a summation. Now if we sum up, so here I'll sum j equals 1 to I minus 1 of j. So here I would use the formula for my summation, except it's going to be I minus 1 times I minus 1 plus 1 over 2. So this length is given by this formula right here. So it's basically I squared minus I over 2. Right. So we can divide this nomen g sub I into 3 pieces. This piece is going to have area I squared, right? And then this piece, so this is I squared right here. Right, because we have I times I. Now the piece over here is identical to the piece down here. And both of them is equal to this length times I. So the area here is going to be I cubed minus I squared over 2. And the area here is I cubed minus I squared over 2, because it's just this formula times I. So when we add those 3 together, well, we get I cubed minus I squared over 2 plus I cubed minus I squared over 2, which just gives us I cubed minus I squared. So that's the sum of these 2 pieces, and then plus I squared. So the whole area is just equal to I cubed. So the area of this boomerang is I cubed. So when we sum 1 through n of I cubed, we just get the formula on the right. So that's a very nice little geometric proof of this final example summation formula.